Sam will stamp your assignment 1.3, which starts with like system, open system, closed system vocab, and has study goals 16 through 24. Please make sure you have a heading or Ruggieri will just skip you. If you want credit, label your homework like that. Second Next, a couple of quick announcements. Tomorrow I will be absent. You should know that I don't usually miss school unless it's a movie day, which is something that the substitutes can usually do, or it's a test day, which is something that the substitutes and my student aides can always do. Just FYI, in the last 5 years, I've only missed 1 or 2 days of actual instruction. And on those days, I talk to my iPad and upload the videos so that I'm talking to you from the monitor. It's pretty Max Headroom, which is a classic old sci-fi series. On movie days, it's your job to answer questions, so please look up. Wednesday I'm gone, you watch a film and answer questions blah 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 through blah 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 in 1.4. That also includes the reading packet. So on Thursday, we will go over your answers from the movie to make sure that everybody saw the film. Reading packet is 25 to 29. The movie is questions 30 to 41. So tomorrow in class, you answer 30 to 41 while watching the film. Do the reading packet at home. That's assignment 1.4. We'll go over that on Thursday when I get back. Then we'll plan for the exam, which you take on Friday. Are there any questions? Yeah.
So the Earth Day thing? The
After school film, tomorrow at 6 p.m.
Yeah.
Are there any questions about that? Any questions about the extra credit stuff we discussed yesterday? Yeah?
Can you do comics?
No. This has to be scientific literacy stuff. So something about data. Yeah.
What's the movie playing tomorrow?
It's called Earth Days. I'll try to put up a trailer on the book face. It's a movie about the history of the environmental movement. Just sort of like an introductory film. Who else? What else? Yeah?
So tomorrow's movie would answer questions.
Tomorrow's in-class movie is questions 30 to 41. One more. Okay, where did we leave off on 1.2? We have finished the vocab and that's all?
No, because we talked about what science was.
Oh, we did number 10. Talked about what science is.
And we talked about popsicle too.
Oh, cool. I thought of a way to discuss science today. The first period we hadn't gotten this far, so I said something differently in period 1 that I think is a good way to make my point. So I'm going to go back to number 10 really quick. Think of science as an argument, where people are like trying to decide who's right. That's science. If you're looking at a fruit, and somebody says, that's a banana, and you say, no, that's an orange, you could figure out who's more right. Do you agree with me? You'd be like, it's kind of yellow and elongate, or it's kind of round and orange. And you could look at it, and you could ask a series of questions to figure out who's right. She says banana, she says orange. We could all come up as a class with a way to help them figure out the truth of this situation. We could say, does it like peel open like this and have like a fleshy white interior? Is it like kind of acidic in the peel? Feel kind of waxy? More or less round? Is it elongate? And we could come closer to answering this question and we could settle their argument. We could be like, oh, well, it's looking more like you were right, it's a banana. Or nope, evidence seems to suggest this is probably an orange. That's science, actually. On the other hand, if it's like behind a wall that nobody can see on the other side, nobody can get around that wall, you're never going to settle this. Do you agree with me? On the other side of this giant impenetrable wall, there is a fruit. I believe it is a banana, and you believe it is an orange, and that's the end of the conversation, because we will never find out any of the facts required to get closer to truth. That's a belief system. Y'all understand me when I say this? Because I've got this pet peeve. When people say that they don't believe science, like, that's just the wrong word. It's like, hey, look, this is a coffee mug. I don't believe this is a coffee mug. What do you mean you don't believe? It has a handle. It holds coffee. I do not believe. Well, do you want to argue? Because we can have a discussion. Do you think it's something else? What is it? Please tell me. We can discuss. I want to argue. We can find truth. Here is the thing that we're trying to identify. I do not believe. This has nothing to do with belief. Science is not about beliefs. Believing is for the stuff where you cannot pursue the truth. You cannot know for sure. When people believe in things, that's cool. I don't mind. I believe in things. You can believe in things. But belief is not science. Those are different pursuits of the intellect. When people say they don't believe in climate change, I tell them I don't believe in bunny rabbits. Take that. Like, who doesn't believe in gravity? Like, if you think it's something else, call it something else. If you want to have a conversation about the data, let's have a conversation about the data. If you want to dispute the science, feel free. That's what all science is. We're all trying to get closer to the truth. Dispute. Debate. Good. That is science. Be very careful when people say they don't believe in science. They're just using the wrong word. It's like people say, I can't see that sound. Well, of course. Those things don't go together. It's just nonsense talk. Don't believe in science? You stupid. That's the wrong word. It's not a matter of belief. Okay, we done with this? I have to vent a little bit because I have this like very serious pet peeve about people mixing beliefs and sciences. Okay. Do you know anybody else who doesn't believe in bunny rabbits? Doesn't believe in gravity? Number 11, the crop circles thing. We saw the crop circles. Somebody make a crop circle for you? Remember, people are dumb. Number 12, measurement is a perfect example of how the public misunderstands science. What do scientists know about measurement that the public does not?
It's not completely accurate, it's only an estimation.
That's right. And by the way, there is no perfect measurement. There's just better measurements. You want to find out how tall I am, I'm about 5'11". But if you get a better ruler, I'm like 5'10 3/4. And if you get a better ruler with like a really fine dial caliper at the end, I'm probably 5'10.789. And if you get an even better caliper, you might be able to add a few decimals, but that's never over. All measurements, everybody says it's an inexact science. All science is inexact. Yeah.
Wait, like, if you said all science is inexact, but then it's all true. Like,
It's all the approach to truth. This is an asymptotal activity. You're trying to get closer and closer, but you'll never have perfect. You understand what I'm saying? That's why science is never over, you know, like, now you can measure that better, and now you can measure it better, and now you can measure it better, and now you can measure it better. Everybody gets all pissed. Like, how come scientists don't have perfect predictions of the future? Seriously, like, people say that there is no climate change because that one guy made that one prediction that was wrong that one time. Like, hold on a minute. Like, it's all like, we're just trying, you know? Like, we're just trying. Okay. Oh, number 13, make a note, goes with number 24. So in two different areas, I discussed that same topic. Looking at number 13. Why does the scientific method not apply? And by the way, how many of you spent the entire 8th grade memorizing the scientific method? Waste of your time. Science doesn't work like that. Not just this one, but essentially none of the sciences work by the usual scientific method, except some types of chemistry and physics where you do very specific question and answer stuff. But why does the usual way to think about science not apply to this one? There's like 3 big issues that make environmental science very unique. Number 1, yes?
It's really hard to have a control in an open field.
Yeah, it's basically impossible. You know, we could answer this climate change question really easily if we had another planet. Because you could just burn a bunch of fossil fuels on one of them and none on the other, and then see how much of climate change is caused by the fossil fuels, right? That would be a really simple experiment. You know, if you have like 2 aquariums, you put 10 guppies in this one, 10 guppies in that one, leave this one alone, and let's find out if bleach kills guppies. Oh, guess so. Because in this one, no bleach, they're fine, and in this one, bleach, they're dead, so we have answered that question. We had the control group and the experimental group, and we manipulated the bleach concentration until we saw an outcome. Okay. So easy. But of course, when we ask environmental questions, it's always, I wonder if bleach will kill me. Imagine you're trying to find out about anatomy by cutting yourself open. That's environmental science. I wonder if this will kill us. It's a pretty interesting experiment. Hello, Mr. Sandoval.
Good morning.
We have 31 enrolled juniors normally, but one of them is absent today. And our 1 enrolled senior is present today. So 30 of 31 juniors and 1 of 1 senior. There's another reason why environmental science is such a difficult and unique practice. Anybody know? Yes?
Just most ecological processes last longer than human life.
That's right. That's right. We won't see the outcomes of our actions in our own lifetime for the most part. And we are manipulating cycles which go in some cases on the millennial range or even millions of years, the geologic time scale.
Ecological processes last longer than human lifetime.
It is a singular, we only have one experimental set, long time frame, and finally super complex system that we're living in while we do the experiments. So really environmental science is just trying to figure out what we're doing and hoping it's not too late. That's like all environmental science. Should I keep pulling on this, or is it my heart? Like, it's very easy to find out if the gun was loaded when it's too late. This is environmental science. Most of our certainties about the environment we found out when it was like, oh, dang it, that was my liver. I kind of needed that. Wonder how I can keep going. Very unique science that we are in. 14 and 15 were not questions. Unless you have questions, I will assume that you've understood them. Questions about 14 or 15. So we go to assignment 1.3. In the vocab, there's a few things I want to point out, just a couple. First of all, please note that open and closed systems are not absolutely possible. They are both extremes. All systems fall somewhere in the middle. So nothing is truly perfectly an open system, and nothing is truly perfectly a closed system. You just say it's either more open or more closed. A river is more open and a lake is more closed. Rivers still have some resident stuff. Lakes still have some inputs and outputs, but one is more open, the river, because the water is moving through and so a lot of material is moving through. Whereas a lake is more closed, it has mostly resident water and mostly resident material. So these are extremes, and none of them is perfectly possible. Questions about that? To discuss uniformitarianism, I got to tell you a story about a dude whose name was Charles Lyell. And when people told him that the Earth used to be really different, but now it was like this, he didn't really like that explanation. He said, how did the Earth get to be like this? And people who knew about science said, well, bro, the baby Jesus made it like this and started the ball rolling, and now it's this way. But at some point, it wasn't here at all, and then it was just made. And that's when everything started. And he was like, well, I have this different idea. Charles Lyell, L-Y-E-L-L, was a really big deal because he suggested what's called uniformitarianism. Your vocab word, uniformitarianism. Charles Lyell, L-Y-E-L-L. He said, I'll bet you the processes we see today were the same in the past. So geologic forces of the present were also going on before, so the Earth was made by the stuff we see around us. He said if it rains now, And that carves holes in rocks. Maybe it's been raining for a long time and that shaped the rocks. And if wind blows sand around right now, maybe wind has been blowing all the sand around forever. He says, if sediment is turning into rock right now, maybe sediment has been turning into rock forever. If glaciers are up in the mountains and moving a little bit, maybe they've been moving for a long time, and that's what's carved these giant valleys. The idea that the present geological forces explain the geological past. Uniformitarianism. Because he was the man who invented glacial science, they named the tallest mountain in Yosemite after him, and I named my son after that mountain. Lyell, that's my son's middle name. His name is Tobias Lyle. In Yosemite, there's Lyell Peak, the Lyell Glacier, and the Lyell Fork of the Tuolumne River. I gotta warn you, students confuse uniformitarianism, just so you know, does not equal environmental unity. Different. That's the idea that all living things are interconnected. Like John Muir said, when you pull one thing out of nature, you find it connected to everything else in the universe. Famous quote by John Muir. That is environmental unity. Okay. Anybody want to talk more vocab? Study goals of 1.3. Ambocelli, I got nothing to talk about, and 17 is the warm-up. Yes?
So, positive feedback is like, kind of has like a negative outcome?
Not really, and I got to be really clear about something. So, in your question, I have something I want to talk about, and then we'll get back to it.
Okay.
So, like, that's a really nice skirt is like a positive comment, right? And like, bro, your hair looks kind of nar-nar. Is like, maybe slightly negative, like, bro, your hair looks horrible. That's kind of like a negative comment. If I say, you can do it, you're a winner. Or you suck, you're a loser. Like, one of those is positive and one of those is negative. Right? Just so you know, that's got nothing to do with this positive or negative. This isn't good or bad. This isn't beneficial or detrimental. Like when you said negative outcome, that's not the kind of negative we're talking about here. It's either good nor bad. Really good things can have negative feedback, and really bad things can have positive feedback. It's not good or bad. This is not things we like or don't like. This is not value judgment. It's just a mathematical thing. Yeah?
I think I found a typo in the book. It says air pollution will shift the population. It says air. Or do we have a book that I can see? It's figure 3.8 line 6.
Try it.
All right, let's see.
While you're looking for it, what is positive feedback and what is negative feedback? We need to agree because this is like a key term. It's on the AP test. People get confused. Yeah.
Positive feedback is an increase to an output that leads to a further increase in the output.
An increase
To an output.
of an output leads to more increase of the output. Yeah,
And then negative is an increase in an output leads to a greater decrease.
that's right. That's right. Yeah.
All right, so it says the right side of the figure shows that increases in air pollution, disease, crime, and discomforts or traffic tend to reduce the city pollution. So air increases
Yeah.
in pollution reduces pollution.
Yeah. Because people move away.
Oh, so okay. So I was thinking if people move away, so reduce the population.
Yeah.
Okay.
Oh, and by the way, that may have been what they meant.
Yeah.
Maybe they meant population. Yeah, that's interesting. Yeah, is it just about population size? Right, you're right.
The other ones were about population size because it was.
Oh, then you're probably right. You're probably right. That is a typo. Population goes up, causes horrible conditions that people run away from, and population goes down. That's a negative feedback. Where population growth leads to population shrink, negative feedback. Because the output lowers that output. Growth in population makes pollution, that lowers population. It's not a self-fulfilling cycle. It's not self-perpetuating. That's negative feedback. I'll give you a separate example that's also about population. Everybody moves to the city, so everybody else thinks there must be something good in the city, so they all move to the city. So everybody else thinks there's something good there, so they all move to the city. So everybody thinks there's something good there, so they all move to the city. That's positive feedback. I'm not saying it's good or bad. I'm just saying that the output makes more of the same. Does that make sense? Like a snowball effect.
So positive feedback is always going to be
Increase.
like increasing of something, and then like increasing.
That's right. This is more of the same.
Okay.
That's positive.
Because of the increase, it increases more.
Yeah, exactly. Because of the increase, it increases more. That's really well said. Yeah, precisely. That's positive feedback there. Negative feedback is self-regulating.
It's like if your bath was too hot and you put in cold water, that'd be negative feedback. You're trying to lower the temperature.
Yeah, I guess so. Yeah. Yeah. So imagine I get depressed, so I eat some ice cream. My wife says, "Your jelly roll's getting bigger." And I go, "Oh," and I get depressed. So what will I do?
Get more
Eat
ice
more
cream.
ice cream.
So what will happen to my jelly roll?
Get bigger. And then you'll get more.
So what will happen to my mental state?
You'll get more depressed.
And then I will.
Get fat.
Is it positive or negative feedback?
Positive.
Positive feedback. Okay. Do you like my example? Jelly roll. Kind of a big jelly roll. My jelly roll goes away in the summer because I get like super active, and I come back from the Sierras and my metabolism's like, and my activity level's like. So in like 2 weeks, I'll put on like 10 pounds. He's no joke. By the way, there's like a persistent misunderstanding that positive and negative is value systems, like things we like or things we don't like. Like, oh, that causes more cancer? That's got to be negative. And like, actually, not just because cancer is bad. I mean, this is just about more of the same or self-regulating. Oh, the rule of 70 will ruin your life. The funny thing is, it is like the simplest thing, and it's so simple that everybody goes, so I don't get it. It's like, no, really, it's that simple. And everybody goes, wait. So what the? And I'm like, no, it's really that simple. Let me give you some warnings. Warning, this will be on the test on Friday. I never tell kids what's on the test on Friday. Second warning, this will be on the AP test in May. This is so simple that a lot of times people go, wait, because this is like 3 words, and everybody's like, wait, what's the trick? I'm like, there's no trick. That's all you gotta know. So you can understand that some things stay the same size forever and some things grow. Like populations usually grow, rocks usually stay about the same. And populations grow at a certain rate. It's called the growth rate. How many of you have seen that equation? Yeah, perfect. Okay. For those of you who've seen this equation, did I get a variable wrong in there? Is it PT? What? Okay. So, if you solve for this one, meaning starting thing to double, if you solve that, you get in other words, the time to double is 70 divided by the growth rate. For those of you who speak math, there's the derivation. But for those of you who speak math, shut up about where it comes from. For everybody else, this is so beautiful. You only have to memorize like the teeny little thing, and you can answer so many questions. 70 divided by the growth rate as a percent is pretty darn close to the doubling time. So, I'll give you an example. If human population is currently growing at 2.2%, our planet will have twice as many people. Anybody know what that answer is?
It was 2.3 on me.
Yeah, okay. Oh, what is that? In 31.8 years. Here's what I did. The growth rate written as a percentage, 70 divided by the growth rate written as a percentage, tells you how long it'll take to double. All you got to know is the growth rate, take the double time. That's the time it takes to double.
You don't have to make it like 0.023.
No, you don't have to make it 0.023 because it's the doubling time written as a percent.
Okay.
Yeah.
How do you figure out how to know like what a quadruple is?
Okay, we can do that. I put $100 in the bank. Let's do a really simple number. Can we say a 7% growth rate because it makes this super easy? At 7% growth rate, how long until I have $800? Take a minute. Do it on your paper. $100 at 7%. How long until I have 800? Do it on your paper. By the way, this is like the last time I'm going to be helpful about this. It's on the test on Friday. It's on like 5 tests on the way to the AP test, and then it's on the AP test. Guarantee you it's on both finals. This is like everywhere. And I can help you, and you can do this, but I want you to try on your paper now, something. I don't care what your answer is, but make an answer. I'm just telling you right now, that's the growth rate. That's GR, written as a percentage. That's it. How long until we have 800? Starting with 100. Oh, Sam or Gary, will you please add all of these aids to my aid group? How many of you think you have an answer? How many of you need more time? How many of you have no idea what the hell I'm talking about? Who thinks they have an answer? How many years?
30.
How many people said 30? Who has a different answer? What's your answer?
42.
42 years. How many people have 42? Okay, who has a different answer? Yes. 20 years? How many out of 20? Has a different answer. Yes?
80.
80. Understandable. How many people have 80? Okay? You say you have an answer?
I have 8.
8? How many people have 8? Different answers? First, does everybody know what the doubling time is? Remember, it's always the number 70. That's the rule of 70. This is a rule. I'll even title it. This applies to the growth of things that grow. So anything that's growing, if you know the rate, I'll give you the time. If you know the time, I can give you the rate. That's the rule of 70. There's only two variables, the growth rate and the time. You must write that down. Everybody has to have that. It's called the rule of 70 for anything that grows. Given that it'll double in 70 divided by the growth rate, and knowing that our growth rate now is 7, watch. 70 divided by the growth rate is 10. Agreed? That's where the 10 comes from. Would anybody like to change their answer? You're changing to what?
To 10.
To 10? We're going to go from 100 to 810.
Oh, no.
That's what I mean. So, who wants to change your answer from 100 to 800? Yes.
30.
30? Well, anybody want to change another answer, a different answer? Watch. In 10 years, my 100 will do what?
Double.
Double. To what?
200.
How long did that take?
10 years.
Have we reached 800 yet?
No.
So what's going to happen in 10 more years?
400.
How many years does it take to get from 100 to 800 at 7%? Because 400 doubles in another 10, because 10 is the doubling time. So we go from 100 to 800 in 10, 20, 30 years. How long to go from 100 to 1600 at 7%?
40.
Now we're getting somewhere. A lot of people go, oh yeah, 10 years and that times that means you have to add 8 times. But this isn't adding, this is doubling. These are like powers, not arithmetic. Yeah.
What if we have a question like, how long will it take to get to like 350?
I would not give you that question, and neither will the College Board. That's the beautiful thing. The rule of 70 only has 2 options, growth rate and doubling. What else? Coincidentally, if you were to graph this, you would get a logarithmic growth curve, and so you could use that graph paper, if it's fancy graph paper, to get how long it takes for 350. It's probably just saying about 18 years, 19 years. Anybody want to talk more about this? The rule of 70 is guaranteed to be on the AP test and guaranteed to be on my test this Friday. And it only has 2 variables. Growth rate, written as a percent, the doubling time. Yeah?
So for the second part of the problem, you just multiply 31.8 by 2 to find the growth time.
So for the second part, how long would it take to quadruple at that growth rate?
Yeah.
Yeah, because you double on one and then you quadruple it the second. So you need 2 doubling times. 1 to double and 1 to quadruple. Right? Anybody else? If you ask questions, I'm here to help you. I'm a horrible math teacher, but I'm willing to do this because I know the kids will be like, wait, what? And like, I get it. I'm not judging you, but you got to ask something if you want my help. Yeah.
So going back to the human population, when you get 31.8, can you write that out? Like, what's to get to, like, if you quadruple it?
Sure. Whatever human population is, will have doubled in 31.8, right? And so that'll double. What happens when you double 2 of the population? You get 4 of the population, right? So in the next doubling time, that'll get up to quadruple what you started with.
Just apples.
Yep. So to go from the current to quadruple would be 2 of these.
So like no matter what it is, like no matter what the original number is, if it's like at a growth rate of 2.2%, it's always going to take 31.8 years.
Yeah.
Correct.
Yeah,
Like,
yeah. I mean,
always.
no matter what, if you're growing a muffin top at 7.7%, at 2.2% growth rate,
Always take.
your muffin top will be double the size in 31.8 years, and that's a fact. By the way, if that's 2.2 per day, then it'll be 31.8 days. So this is assuming an annual growth rate to make it years, like you call it a minute growth rate to make it minutes.
Will like on tests and stuff, will they potentially put it in other than years?
I think you just got to remember that the units stay the same.
Okay.
So whatever unit you're talking. Yeah.
Maybe this is just like the bacteria problem that we do next.
Say, come on.
This is kind of similar to the bacteria problem. That was the next question.
This is the bacteria problem that was the next question. Yeah, exactly. The one problem is that that one has a typo.
Yeah, but
They cut out the word another. But what? You want to do that one?
Yes.
Fine, Mackenzie Bell, but other people want to do the other one.
I just meant once you did this, it made sense.
Oh, really? Good. Okay, watch this. Number 19 has a typo. It should have said, if the bacteria found another 12 at 12:02, in other words, how long will it take to fill a total of 16? But you don't, the homework you did is great, but the book had a typo, so watch. Let's do it from scratch. You have one jar at 12 o'clock. Is that right? And they double every minute. Do we agree? Yes? So at 12:01, how many will you have? What?
Double
2.
when you started.
Because it doubles. That's 12:01. Agreed? And at 12:02, how many will you have?
4.
And at 12:03, how many will you have?
8.
And at 12:04, how many will you have?
16.
These are my jars. Don't judge me. This is the very interesting problem when people talk about all the jars on Earth and stuff. It wouldn't take an extremely long time to run out of the planet, no matter what growth rate you've got. Because sooner or later, you're adding a whole bunch of jars. In a couple more minutes, you're adding 32, and then in a couple more minutes, you're adding 128, and a couple more minutes, you're adding 600 and blah, 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 blah. When people talk about like, oh, when we run out of space, we'll just go to Mars. Like pretty soon you can't travel fast enough to find enough planets to double into. Because you're doubling by 2 planets pretty soon, and then you're doubling by 4 planets pretty soon, and then we don't know where all the planets are. You know what I'm saying about this? Exponential growth. It's like a really classic mathematical phenomenon. We'll come back to discuss this at another time. Anybody want to talk more about this?
So that one would be 4 minutes.
What's that?
The answer is.
Yeah, I think so. It would fill a total of 16 by 1204. I don't think it helps to predict details of questions anyhow, but I don't know. The answer is I don't know. I reserve the right to ask you any question that tests concepts. So, I don't know that there will be, but I'm sure that there could be, yeah. The only equation is this one, or times 2 times 2 times 2 times 2. Okay. Oh, by the way, does anybody know the growth rate of this population? If it doubles in 1 minute?
200%.
No? Yes. How'd you get that?
You set the equation equal to 1. It has to be over 70.
Watch. If you know the doubling time is 1, then what would the percent have to be? It's 70% per minute. Yeah. Does that make sense? That's the growth rate of that population. Fill in the jars. Because then they're going to double in a minute, and they're going to double in a minute. Okay. Beautifulness. Oh, number 20, environmental unity. Anybody know what environmental unity is? Yes?
Basically, if you change something, other things are going to change
Yeah. Because
it's
what?
always going to affect something else.
Yeah, yeah. You know, you got to remember that the environment is basically a single set of stuff. So if you're adding something on one side, it means you're taking something from somewhere else. In other words, everything is connected to everything else. John Muir said it really well. He said, if you pluck out anything in nature, you find it tied to everything else in the universe. We'll talk a great deal about environmental unity in this class. Yeah?
I had a question on that one.
Yeah, sure.
When it was talking about the unity between the salmon streams and the redwoods,
Yeah.
what was that?
Well, who would have thought that cutting down trees affects salmon, and vice versa? Who would have thought that getting rid of salmon affects trees? But the surprising thing is, if you look carefully enough, you can basically find connections between all sorts of stuff. So the connection between the trees affecting the salmon is that trees filter water and prevent erosion, and so when the trees are gone, you have a lot of soil in the water, and the clarity of the water goes down, and the fish can't get their food, and they can't make babies, and so salmon populations suffer when the trees are gone. And on the flip side, even more surprising, when there's no salmon, there's nothing for the bears to eat, and bears pooping fish oil is the largest terrestrial fertilizer on Earth. Not just pooping fish oil, but also tearing apart the fish and leaving the parts they don't eat. So a bear goes to the river, eats a fish, walks up to the hill, eats the good parts and leaves the rest, and then takes a dump and goes back to the river. That's a lot of tree fertilizer. The largest terrestrial fertilization system is bear poo and salmon remains. So go figure. Salmon help the trees, and the trees help the salmon. So number 21 is like a really good question that's really hard to answer for me. People talk a lot about the balance of nature and natural balance, and we're going to disrupt the balance, and there was once a balance, and now we've lost the balance, and we're in balance, or we're out of balance, or balance, nature, balance. And that's actually like the stupidest phrase ever. You know, like, if you watch a seesaw doing this a lot, going up and down, up and down, up and down, the average is that the seesaw is balanced. Even though it is dynamic, it's moving a lot, it's going up and down, but the average is at the middle. Does that principle make sense visually, like the seesaw thing? Know anything about seesaw? Here's another one. Deer populations go up and down like this. Wolf populations go up and down like this. The way that it works is, if deer population goes up, then there's a lot of deer for the wolves to eat, so wolf population goes up. But as wolf population goes up, they start to hammer all the deer. So eventually all the wolves will starve, which lets the deer bounce back. Which lets the wolf population spike, which causes the deer population to go down. You guys know that? It's called the predator-prey effect, like that. So the funny thing is, if you step back, it seems like wolf and deer populations are balanced. When in reality, they're both going up and down, like a seesaw going up and down. A lot of times we think that nature has this special magical balance, but that's not true. That's just the outcome of a really dynamic system. Be careful. Anytime that you think you're looking at something which is balanced, you're probably just looking at something that's going up and down, and you're just seeing it at a moment of average. Yeah?
What word would you use to describe that?
It's called a steady state equilibrium. So, like, in our lifetime, it looks like ocean's always at a certain level. But if you look at the glacial period, there's more and more water living in the ocean at times, and more water living on land as ice. And so the average looks like balance, but if you step back, you're probably just looking at a moment within a steady state equilibrium. Does that make sense? Oh, 22 I can skip, and 23 I really want to talk about, but is the bell ringing and like right now?
Yeah. We talked about 23.
You know, I can do this in 1 minute. Number 23 is, what's the Gaia hypothesis? Just so you know, it was a really tempting way to think about the planet in the 1970s that was totally bogus. People thought that the planet had this like life energy and consciousness that was balancing everything out. That the planet was called Gaia, and I guess we'll have to talk about this later.